Welcome, Calc class, to Lesson 1-5, where we're going to discuss infinite limits. Before we formally talk about limits, I want us to quick look at the definition of what a limit is. We define a limit by saying let f be a function defined on an open interval containing c, except possibly at c, and we're going to let L be a real number. If we do that, then we can say the statement the limit of f of x as x approaches c is equal to L. What that means is that for each epsilon, which is a Greek letter we're looking at, that is greater than 0, there exists a delta value that is greater than 0, such that zero is less than the absolute value of x minus c, which is less than delta, then the absolute value of our function minus L is less than epsilon. We need to know this when we're talking about infinite limits. Now, this may already be in your notes from our lesson on 1-2, solving limits graphically and numerically. So now we're going to get straight into the definition of infinite limits. So the definition of infinite limits states, let f be a function that is defined at every real number in some open interval containing c, except possibly at c itself. The statement the limit of f of x as x approaches c is equal to infinity. What that means that for each m value that is greater than 0, there exists a delta, I'm just going to use the lowercase d for that, delta greater than 0, such that f of x is greater than m whenever zero is less than the absolute value of x minus c, which is less than delta, we can say similarly the statement the limit of f of x as x approaches c is equal to negative infinity, that means that for each n value that's less than 0, there exists a delta that's greater than 0, such that f of x is less than n whenever we have 0 less than the absolute value of x minus c less than delta. And that's not the end of the definition. We have one last part. So to define infinite, or the infinite, limit from the left, what we do is we replace the 0 less than absolute value of x minus c less than delta by c minus delta is less than x, which is less than c. And then to define the infinite limit from the right, we're going to replace the same thing, 0 less than the absolute value of x minus c less than delta, by c is less than x, which is less than c plus delta. Something to keep in mind, what we're saying is with the limit of f of x equals infinity, we're not saying that that limit actually exists. What we're saying is that it tells us that the limit fails to exist by telling us that there's unbounded behavior as x, or as f of x is approaching c. So let's actually look at our first example, example 1, where we're going to determine infinite limits from graphs. So give me a second and I'm going to have the graphs here on the screen. So here's the first example we're going to do. This is a rough picture, it's not perfect, of the graph of f of x equals 1 over x minus 1 quantity squared. So when we're looking at this graph, what we're going to do is we're going to look at the limit as x is approaching 1. So let's write that, the limit of 1 over x minus 1 squared as x approaches 1. If we were to just use direct substitution, we would get something that's undefined. From looking at this graph, if we follow the left and right bound behaviors, we continue as we approach -1 to just continually increase. Now, back in lessons 1, 2, 1, 3, we said that in this case the limit's not going to exist, which isn't exactly true. What's happening is as our x values get closer and closer to 1, our y value is getting closer and closer to a value, but that value we don't know. We're going to call it infinity. All it means is as we get closer and closer to 1 on the x, our y continually gets bigger and bigger. Let's look at another example. So again, this is a rough sketch of f of x equals -1 over x minus 1. Let's talk about this in a couple different cases, because as we're approaching the asymptote 1, we're approaching from two different sides. So we're going to look at the limit of -1 over x minus 1 as x approaches 1 from the right. We're also going to look at the limit of -1 over x minus 1 as x approaches 1 from the left. So let's start with the right. And I'm going to use a blue arrow for our right bound. So as we are approaching from the right on our x, our y starts to dip down. When our y starts dipping down like that, in our right bound limit, we're going to actually not approach infinity because our y values are continually getting smaller. We're approaching negative infinity. Let's also look at what the left bound behavior does. I'm going to do that one here in red. As we get closer and closer to 1, our y's continually increase. In this case, our limit from our left bound behavior is infinity. In this case, if we were asked, which I'm not going to ask you to do, but if we were asked to find the limit of f of x as x approaches 1 without any left bound or right bound constrictions to it, this one we would have to say it does not exist because of the whole two different end behaviors. So there is something that was familiar in those graphs that we just looked at, and those were asymptotes. So we're going to talk about vertical asymptotes. So first, let's look at the definition of vertical asymptotes. We define a vertical asymptote if f of x approaches infinity or negative infinity as x approaches c from the right or the left, then the line x equals c is a vertical asymptote of the graph of f. While we're at it, let's also look at our next theorem. Theorem 1.14, which is we're going to call the vertical asymptote. So what we're going to say is we're going to let f and g be continuous on an open interval containing c. We can then say if f of c does not equal 0, then g of c is equal to 0. And there exists an open interval containing C such that g of x cannot equal 0 for all x values that do not equal C in the interval, then the graph of the function h of x equals f of x over g of x has a vertical asymptote at x equals C. That is theorem 114. So let's look at example 2, where we're going to find vertical asymptotes. So first we're going to look at h of x is equal to 1 over 2 times x plus 1. What we're essentially doing when we're trying to find a vertical asymptote is we're looking for what x value would we plug in to our denominator that would give us a denominator of 0. So let's just take our denominator, 2 times x plus 1, and we're going to set it equal to 0, and we could solve it for x. But this one is actually fairly simple. There's two outcomes. In fact, only one. We need to make sure x plus 1 equals 0, and in order for that to happen, x has to equal negative 1, which means our vertical asymptote for our function is going to be x equals negative 1. Let's also look at another example. We'll call it B, where we're going to have our function h of x. It's going to equal x squared plus 1 over x squared minus 1. And again, we don't want the denominator to equal 0. And there's a couple methods we could use to find what x values would make that denominator be 0. One method, you can just take x squared minus 1, set it equal to 0, and use the square root method to solve for x. In that case, we would add 1. X squared would equal 1. And then we can take the square root of both sides. And the square root of 1 is 1. So here, we could say x is equal to positive 1, but the square root of 1 isn't just positive 1. It's also negative 1. So x is going to be plus 1 and minus 1. Another possible method we could have used is we could have factored x squared minus 1. This is a difference of 2 squares because we can rewrite this as x squared minus 1 squared. We can replace that b term with 1 squared. And that's going to factor to x plus 1 times x minus 1. And if we were to set each of those factors equal to 0, we would again find that x is equal to negative 1 and positive 1.